In this video, we are going to talk about the characteristic curves of the enhancement in MOSFET. And basically, we have one interesting relation that we are going to focus on, which is the relation between IDS and VDS. And let me tell you honestly that if you remember this relation or this set of curves that we are going to plot here between IDS and VDS, then you know everything about the enhancement MOSFET in MOSFET. Okay, so if you can keep this figure that we are going to plot in your mind, then you will be able to understand the operation of the enhancement in MOSFET perfectly. In addition to the equations, of course, you need to memorize some equations. Okay, but here tells you like how the transistor works exactly. Okay, so let's start. We said that the transistor is off as long as VGS is less than V threshold. So if you have VGS less than V threshold, then we will get a curve at the zero. So we have a zero curve here. So that zero current, it happens as long as VGS is lower than or equal to V threshold. Sometimes we call it VT, sometimes we call it VTH, sometimes we call it VTN because we are dealing with an NMOS transistor, okay? And this threshold voltage, usually for the enhancement NMOS, usually it's in the range between 1 and 2 volts. So it's between 1 and 2 volts. So as long as VGS is less than V threshold, the transistor is off, the current is 0. If you increase VGS above V threshold, the transistor will start to be on. And the transistor will start to be on. And when the transistor is on, we have two regions. A region when VDS is lower than a certain value, and another region when VDS is greater than a certain value. So when VGS is greater than V threshold, we'll start to plot a curve with VDS between IDS and VDS. When VDS is smaller than a certain value, let's say that we are going to take a certain VGS, let's say 4 volt, okay? Then as long as VDS is less than 4 minus V threshold, let's say that this is VGS minus V threshold, okay? As long as VDS is lower than VGS minus V threshold, we'll be working in the triode region. And when VDS is greater than this point, which is VGS minus V threshold, will be working in the saturation region. So this is for VGS equals 4, and let's assume that V threshold M is 1. So this value will be 3. For example, this is just an example. Okay, this value will be 3. So as long as VDS is below 3, okay, then this is the triode region. If VDS is greater than 3, this is the saturation region. In the triode region, we called it the linear region because the current approximately will be in linear relationship with VDS, which means that as you increase VDS, the current is going to increase linearly. So it will take this form. Of course, it's not exactly linear. It has a quadratic relationship. However, for small values of VDS, it takes a linear relationship and then it starts to be quadratic, until we reach to this point where VDS reaches 3, or it reaches the value VGS minus V threshold. Then we enter the saturation region where the current will start to saturate. So this is called the saturation region. The current will be fixed. It will have a constant value with VDS. If you increase VDS, it doesn't increase. This is a curve, a relationship between IDS and VDS for a certain value of VGS. What happens if we increase VGS or decrease VGS? What happens if we change VGS? Again, if we change VGS, what happens? We'll get a similar relationship. However, if we increase VGS, the current is going to be higher. So the current will be higher in the triode region. Okay? And what happens to this point? This point, if we increase VGS, let's say we'll take VGS equals 6, then this point will be 6 minus 1, okay, which is what? Which is 5. So the border between the triode and the saturation will be at VGS equals 5, right? At VGS minus V threshold, and VGS now is 6 minus V threshold 1, it will be 5. So the point between the triode and the saturation will happen here at 5, and then once we enter the saturation region again, the current is going to be fixed or saturated at this point. If we reduce VGS, we are going to get a similar relationship, but the current is going to be lower. So for example, if we take VGS equals 2, then again we are going to get a linear relationship here until we reach to VGS minus V threshold. VGS minus V threshold here will be 1 volt, right? So this is VGS minus V threshold when VGS is 2. When VGS is 2, it will be 2 minus 1 equals 1, right? Once we reach here, we will enter the saturation region and the current is going to saturate, okay, like this. And hence the border between the triode region and the saturation region, it's not like vertical points, it's not a vertical border. Actually, there is a border that looks like this. So the border is itself a curve. The border between the triode and the saturation region, it's a curve that looks like this. As you increase VGS more, the point between the saturation and the triode is going to increase, right? Because the point at which the transistor moves from triode to saturation is at VGS minus V threshold. As you increase VGS, the point at the border is going to move this side. So to the left of this line, to the left of the border, we have the triode region. To the right of this border, we have the saturation region. In the triode region, as you see, the current depends on what value of VGS you are working on, and also it depends on what value of VGS. So if you change VGS, the current changes, and also if you change VDS, the current changes. So we expect that the current equation for the triode region, it depends on both VDS and VGS. And I'm going to give you now the equation. Don't be scared, because as you use it in solving the examples many times, you are going to memorize it. So the equation is a constant Kn multiplied by VGS minus V threshold minus VDS over 2 multiplied by VDS. As I said, the equation, it's quadratic in VDS. However, for small values of VDS, when VDS is very small compared to VGS minus V threshold, you will find that it's approximately linear in VDS. But when VDS increases, it becomes close to VGS minus V threshold, it becomes close to the point where at the border between the saturation and the triode, then the equation will become more quadratic. You will find that it will become a curve, okay? So this is the equation in the triode region. The current depends on both VGS and VDS. What about the saturation region? In the saturation region, the current depends only on, does it change with changing VDS? No. As we change VDS, the current doesn't change, right? But it changes if we change VGS. If we change VGS, the current changes. So you expect that the current in the saturation region, it depends only on VGS. So the equation of the current is Kn over 2, the same constant, over 2, VGS minus V threshold squared. So this is the current in case of the triode region. This is the relation in the triode region between the current VGS, VDS, and this is the relation in the saturation region between the current and VGS. What about the constant? This constant Kn is defined as following. The constant Kn, and maybe this is the scariest part in the equation, is defined as Kn dash W over L. Why it is the scariest part? Because it contains some parameters from the physics of the transistor, right? So Kn equals Kn dash, another constant, Kn dash, W over L. W is the width of the transistor, L is the length of the channel, if you remember from the physical structure of the transistor. What is Kn dash? Kn dash equals mu n C oxide, where mu n is the mobility of the electrons, and C oxide is the capacitance of the oxide layer, the capacitance of the silicon dioxide layer below the gate per unit area. So C oxide is defined as epsilon oxide over T oxide. Epsilon oxide is the permittivity of the oxide layer, it's the oxide permittivity. And T oxide is the thickness of the oxide layer. So this is the oxide permittivity, and T oxide is the thickness of the oxide layer. So as I told you, like it depends on parameters from the physics. So we can control this Kn by controlling the width, the length of the channel, the oxide layer, the permittivity of the oxide layer, the thickness of the oxide layer. We can control this parameter or this constant Kn. So basically you can write Kn, if you are in a hurry, you can write Kn as mu n C oxide W over L, okay, where C oxide is epsilon oxide over T oxide. This is the capacitance per unit area. This is the farad per meter square, okay, capacitance per unit area. So this is the constant Kn, mu n C oxide W over L. Again, don't be scared. With time, with solving many problems, you are going to remember it, and along with the two equations here. So these are the three equations that you will need to memorize in order to analyze the DC circuits of the MOSFET. Okay, so these are basically the characteristic curves for the MOSFET in the triode region, in the saturation region, along with the equations. This is the tree that shows you where the transistor is going to be off, where it is on, where it's going to be triode. Of course, for VDS small, it's triode. If you remember the curve, you remember the conditions. For small VDS, lower than VGS minus V threshold, it's triode. For high VDS, it's saturation. Okay? So these are the basic relations for our transistor. One more thing before we end this video. We remember in the bipolar junction transistor, we talked about something called early effect. That practically speaking, they found that in the saturation region, or in this region in the bipolar junction transistor, it's called active, by the way, it's not saturation. And be careful of this, because many students, they do this mistake. In the bipolar junction transistor, this region was called saturation, and this region was called active. Here, no, saturation is here. Now, in the MOSFET, the saturation is here, not here. Saturation is here, and this region is called the triode. So in the bipolar junction transistor, in the active region, which is now saturation, we used to say that practically speaking, they found that the curves here are not horizontal. They found that the curves, they have certain slope. Practically speaking, right? Same thing happens here. Same thing happens here. They found that in this region, the curves are not exactly horizontal. Of course, I'm plotting it with a big slope here, but they found that they have a little bit of slope. So the curve instead of the line, instead of being horizontal, it has a little bit of slope, which means that it depends on VDS. The current depends on VDS a little bit. Of course, the slope is very small. I'm plotting it here big just to see it, for you to see it. But in fact, in practice, it's very small slope, which means that the current in this region depends on VDS. Why is that? This is called the channel length modulation. Channel length modulation effect. There in the bipolar junction transistor, we called it the early effect. Here we call it the channel length modulation effect. What is the channel length modulation effect? Basically, in our equations, we have this constant, Kn, right? Kn. let's focus now on the saturation, because this is the equation that is important for us, the saturation region. We have this Kn. Kn, inside Kn we have L. We have the length of the channel, right? The length of the channel between the source and the length of the channel between the source and the drain. This is the source, this is the drain. And we have, in the equation, we have L, Kn, and Kn contains L. However, when we enter the saturation region, the channel pinches off. The channel pinches off. And effectively, the length of the channel should be this length, not the whole length. It should be length, this shorter length, not the big length, not the full length. It should be the shorter length. However, in the equation, we use the whole length to make it easy, because it's very difficult to measure what is the length of the channel under a certain voltage of VD. It's very difficult to us to do that. If we can do that, that would be perfect. If we can use the practical L here, the actual L, this will give us the exact equation. And the actual L here, it depends on the voltage that you connect to the drain. As you increase the voltage of the drain, the channel will close more and the length will become shorter, right? So we should use this actual L in the equation. However, because it's difficult to use this actual L in the equation, they modeled it. They approximated the effect of increasing the drain voltage here. They said, okay, let's use in Kn, let's use the full L. Not the actual L, the full L. We are going to use this L, the full length. But we are going to multiply by a factor to take into account the effect of VDS. So what happens is, they multiply by a factor, 1 plus lambda VDS, to account for the channel length modulation. So I'm going to write it in a different color. 1 plus lambda VDS to take into account the channel length modulation effect. Of course, lambda is called the channel length modulation parameter. Okay, lambda is called the channel length modulation parameter, and if it is 0, then this means that we ignore the channel length modulation effect. If I gave you lambda, the channel length modulation parameter, usually it's very small. It's usually very small, okay, because it's opposite to the early voltage. Early voltage was in the denominator in the bipolar junction transistor, and usually it was big. Lambda now, instead of being in the denominator, they put lambda in the numerator, okay, and it's very small. So the effect of VDS usually is very small here. However, it has some effect. If I gave you lambda to be 0, this means that you ignore the channel length modulation effect, and you will use the original equation of the saturation region. So anyways, this is the exact relation that takes into account the channel length modulation and takes into account everything, where here in Kn we use the full length. So you don't need to calculate what is the actual length, because it's very difficult to calculate what is the actual length. So you use the full length of the channel, and then we add this bracket here to account for the channel length modulation. If lambda is 0, then you remove the channel length modulation and you deal with the original equation in the saturation region. Okay? So this is very similar to the early effect in the bipolar junction transistor, and now these are everything. This is everything about the enhancement in NMOS. The regions of operations, the equations, the channel length modulation, and everything that you need to know about the enhancement in NMOS. In the next video, we are going to discuss other types and how we change our equations that we learned here to the other types of MOSFET transistors. See you in the next video.